So far the range and interquartile range basically just use part of data. They're not using the whole data set, right? Because it's not calculating the difference or between each data point, right? So basically, if you change some data point, it's not going to change. So when you compare two data sets, some minor changes in the data point that would not affect the measure of this person, right? Which is range and interquartile range. So the following measurement actually would solve those issues. There's some slight changes in data point, then actually the measurement will change. So the first example, we have the variance. So the idea of variance is looking at how each observation different from the mean. Okay, so that is very clear. That's why we want to calculate difference between the mean. And of course, we want to get all the difference and add them all up, right? And then usually you want to divide by n because you don't want the larger data set to have a larger measure. So it's usually the average different from the mean, right? And that is one measure, right? And but handling the difference, right? You have to take account into different from the mean. You want to take above the mean and below the mean. You want it to be take the absolute value, right? So to take into account, you don't want to cancel it out, right? Because someone is above and below, then you don't want to cancel it out. So you want the absolute value. But mathematics calculate absolute value is a little bit more tricky. Now we can do it, but in the old days, not easy. So one of the compromise to do so is to take square. Okay, so you take the square difference. Okay, so that's why the variance is, the definition is average square difference from mean. Okay, it's from the mean. The typo is from mean. So that's why the notation is add them up, all the difference from the mean and square difference, and take over n, so it's average. Okay, so this is what we call the variance, and this is the mostly common used one. Okay, and very often we don't use this exact form. We will use not divide by n, but divide by n minus 1. Okay, adjustment factor of n over n minus 1. And this adjustment factor will not be crucial when n is big. Okay, so it's more like a small sample adjustment. When sample size is smaller, this adjustment factor is more significant, right? And why is the case we need this one? We will talk about this in later chapter when we talk about estimation, and this one will be much better estimate of what it is. But now it's not clear what is going on, but let's accept that either you divide by n or n minus 1. This is called population variance. This is called the sample variance, but we don't talk about what a sample is, but later we'll talk about this. But for the moment, we just take n minus 1. And when I learned this, I always question why I have this. There's a lot of explanation, but just bear in mind, just keep your curiosity until the later chapters and you will learn about it. So just either n or n minus 1. And when the sample size is large, right, n is 1,000 or 3,000, actually you don't see the difference between the sample part and the one we used to define. Okay, so this is variance. And because you take a variance, you take a square, right? So all the unit will become square, right? So maybe cm becomes cm square, kg becomes kg square. So it's not easy to understand what's going on. So that's why very often we take the square root. Okay, that's called standard deviation. Okay, so we just take the square root, and then the measurement unit will be the same as the original one. Okay, so that avoid the problem of taking the square root. Okay, taking the square, so take the square root and go back to the original one. So that's why the formula is very simple, right? Just this, right? Take the square root. Okay, so that, and the sample one is also take the square root. Okay, so that is very simple. Okay, and once you do this, when you try to compare standard deviation across sample, it's not so easy, right? Because it is still affected by the measurement scale, right? Because when you talk about a data, say for income, you talk about when measurement is a unit dollar or $1,000, okay, or per $1 million, again, can be the standard deviation can be different. Still, you want to, when you compare two group of data, you want to normalize it. So that's why we have a new concept we call coefficient of variation. So then you basically you scale it by its mean. So that's why you divide it by mean and times 100. Okay. So this is the usual way because coefficient of variation is useful to compare when two data sets. There are different mean, different standard deviation, and you want to ask, okay, which data set is more dispersed than others. Okay, so that's the idea. So let's see an example. Okay, so suppose the data set is 2, 3, 4, 5, 6, 7, and we know the mean is 4.5, the number of data size set is 6. Okay, you now try to verify yourself. Okay, the population variance is this number, and sample variation, and all these are these numbers. You need to verify them by using your calculator or using a hand, by following definition, right? For example, I just show you this one, how to calculate this 2.967